Hi everyone, so we're going to be looking at infrared spectroscopy, which is going to be used to identify the bonds present within a molecule. So IR is absorbed by certain types of bonds and it causes the bonds to stretch or bend, and when they absorb certain wavelengths of IR. So these are the different types of vibrations that can happen when the bonds absorb IR. There's different types of vibration, bending and stretching that occurs when the molecules or the bonds will absorb IR radiations. Now, when these bonds undergo the stretching and the bending, if there is a change in dipole during that bending or stretching process, the bond is going to absorb IR radiation and is known to be IR active. For example, CO2. Normally CO2 is non-polar, but when it stretches and when there is bond stretching and bond bending, what happens is that there is a change in dipole moment. So these diagrams can be used to show the vibration. So this is symmetric stretching. So here you don't see any change in dipole. So this is IR inactive. If you look at this type of asymmetric stretching, it is IR active because there is a change in dipole. Here you have bending, symmetric bending here. So you have the molecule being IR active when these types of bending occurs. If you look at H2 and O2, diatomic molecules like these that are non-polar, these are going to be IR inactive because any form of stretching or bending does not result in a change in dipole. So these are inactive. Now, the amount of energy required to vibrate a bond for bending or stretching depends on the strength of the bond. So stronger the bond, more energy is going to be required to vibrate it. And also, the amount of IR radiation absorbed by a bond depends on its polarity. The more polar the bond, the more strongly it's going to absorb IR radiations. So you'll have stronger peaks at higher wavelengths. Let's look at an IR spectrum. Now, when you look at an IR spectrum, you're going to have the wave number and you're going to have the percentage transmittance. The deeper the peaks are, so this is one peak, so the stronger that peak, the more IR radiation is absorbed by that specific bond. And an IR spectrum is divided into two main regions. So at around wave number 1500, this part here, this is called the fingerprint region. This region is difficult to interpret and is unique for each compound. But this part over here, this is where you have the functional group region. And in this region, we can identify the types of bond present in that compound and hence determine the functional groups present in that compound. So the peaks shown by specific groups are shown in a table in the data booklet, section 26, and it shows the type of bond and the wave number at which these peaks will occur, and it will tell you the intensity of that peak. So strong intensity means that you see a strong peak. So this is a peak of high intensity, strong intensity. This is a peak of medium intensity. But among this list, the important bonds that you should be able to identify is the CO bond, the OH bond, the NH bond, this one. So these are the main bonds. Sometimes this is also very useful. So these are the main bonds that you should be able to identify. But you have to remember that these wave number values might not, this range might not be exactly as shown in the IR spectrum. The peak could move to a lower wave number value, or it could move to a higher wave number value based on the surroundings of that bond. What I mean by this is that COH here and OH here, it's showing the same bond, but when it's in the carboxylic acid, you see that the wave number is much lower compared to when the OH bond is in an alcohol. So the polarity, the surroundings of the bond is going to affect the wave number. Let's interpret the IR spectrum of ethanol. When you're interpreting the peaks, the IR spectrum, normally we are going to focus on strong peaks. And we're going to look at the functional group region and then maybe get some information from the fingerprint region. So here when we look at the peaks, we find a strong peak at X, one at Y, and you have a very strong peak at Z. First step, we're going to write the wave number. So this is around. So you have the different wave numbers. They don't need to be exact. It's just a range, like where the peak starts and where the peak ends. So it's just a range. It doesn't need to be exact. Now, when we look at this peak, this is very characteristic to OH bond. So when you look at the data booklet here, so a peak at this region, so it's hydrogen bonding in alcohols and phenols, so it's the OH bond here. So this is due to the OH bond. And if you look at this peak Y, you'll see that kind of peak occurring in most organic compounds, and this is due to the CH bond. If the carbon is attached to an electronegative atom, sometimes this might shift to a lower wave number. But in that region here, you're going to see the CH bond stretching. And in this region at peak Z, this is due to the CO bond. So 1050 to 1410. So you see, you're given a range. So don't be misled by that range, because you see these two ranges, they overlap. So that's why you have to be familiar with what kind of bond you're looking for. So in this case, this is the CO bond stretching. So based on the information, we know that in that molecule, you have a CO bond, you have CH bonds, and then you have OH bonds. Using the index of hydrogen deficiencies, using mass spectrum, eventually you can figure out the structure of that molecule. So in ethanol, we see the bond stretching for OH, for CO, and then for the CH. If you compare the IR spectrum of ethanol to that of propanol, so here you don't see any OH peak. So this is a very weak peak. So we're not going to be interested in that. The peak at A, this corresponds to the CH stretching, and you can see a strong peak here at B, And you also have a strong peak here at around 1750 here. So this is because of the C double bond O stretching, which you can see here. So these are the main stretching that you need to know. You need to be able to interpret. If we look at this spectrum, so you have the formula given to you. From the formula, you can find the index of hydrogen deficiency. So it's 1. So which means that you have one double bond in there. If you look at this peak, this is a very broad peak, which is very characteristic to the OH in a carboxylic. So it occurs at 3000 centimeter minus 1. So it's OH, but because you have that broad area over here, that broad area corresponds to a lowering of that peak due to the electronegative oxygen in that bond. And you can see the peak at B, which is around 1700 cm-1, which is due to the C double bond O. And this peak over here, this is at around 1050 cm-1. So this is because of the CO stretching. So based on this, we can deduce that in the molecule you have COOH. Since there's 3 carbons, so I have 1 and 2. So I'm proposing this structure. If we look at this one, so this peak A is at around 1750. So this is because of the C double bond O. You see the peaks repeat themselves, and then you have this one, which is at around 1250, which is because of the CO. So you see the CO bond will not always occur at 1050 cm-1, but it will occur in that particular range. So when you identify a peak in that range here, you can say that it's for CO stretching. Now when you look at these 2 bonds, so you have C double bond O, and then you have CO single bond. So what is the name of the functional group? This is an ester. Identify which of the following molecules absorb IR and explain your choice. We know that H2 and O2, they are IR inactive because they do not produce a change in dipole when there is stretching or bending of the molecule. But HCl, it's going to produce a dipole. The molecule itself is polar, produces a change in dipole when there is stretching or bending of the molecule. Let's see another one. So C3H6, the first thing we'll do, we'll try to find the index of hydrogen deficiency. Whether the question asks you or not, it's good practice to find the IHD because it's going to give you an idea. So it's going to help you figure out the structure. So the question asks you why it cannot be that molecule. So if you look at this molecule, it's suggesting the presence of OH. But when you look at the IR spectrum, you don't see that strong OH peak that should occur above 300 cm-1. So it cannot be this molecule because there is no OH peak that is in the spectrum. When you look at these peaks, this is due to the CH stretching. Now you have one peak over here at 1780 cm-1, which means that most probably this is a C double bond O. So 1780 So C double bond O, it fits a bit into this range. If we try to see if it could be a C double bond C peak would be at a lower wave number. So it cannot be a C double bond C in it. So the double bond that we identify from the IHD is because of a C double bond O peak. So these are the 3 reasons. The last question on IR. So you have these 3 different compounds. You have to determine which spectrum corresponds to which compound. Let's see the main functional group. So you see the COOH here, and you see COOH produces that characteristic broad peak over here. So most probably this is A. And then we have, so this is C, right? Then we have COO. So this is an ester, and molecule C is a tertiary alcohol. So the OH peak will be present in molecule C, and you can see specifically that OH peak here. So this is molecule C, and in molecule B you can spot that strong CO peak. So this is molecule B. So we've already identified our spectrum, and let's give the reasons. So these are the reasons. So to sum up, when you're interpreting IR, no need to learn that IR table by heart, and no need to rely too much on it. It's very important that you're able to identify the characteristic peaks, OH in alcohol, OH in carboxylic acids, C double bond O peak, C single bond O peak. These are the essential peaks that you should be able to identify at eyesight. Then anything else is just going